Self-organization. Self-organization is a process in which a pattern at the global level of a system emerges solely from numerous interactions among the lower-level components of the system. The rules specifying the interactions among the components are executed using local information, without reference to the global pattern. Cellular automata. Within self-organizing systems, we are looking into cellular automata, which is a discrete dynamical system that consists of an infinite array of cells. Each cell has a state from a finite state set. The cells change their state according to a local update rule, based on their old states and their neighbors. Understanding the natural phenomenon. We are examining foam reduction under different densities of foam with acetone. Acetone is poured at the center and at the edges, varying from single to multiple pouring points in low-density foam. On a particle level, as the liquid seeps in, it starts reducing the particles simultaneously from all sides to form a web-like pattern. This shows how reduction changes with the density of the foam. The behavior of reduction differs in higher density foam as the liquid spreads over the surface before seeping down. Digitizing the phenomenon. We simulate the behavior of reduction in low-density foam. It starts with a cell that only considers the cell below it as a neighbor. In the next iteration, the cell remembers its previous state and retains it. In this case, the cell considers its rough neighbors and starts to branch out. This simulates the behavior of reduction in high-density foam. It considers all 6 neighbors and spreads horizontally first, then seeps down. 3D simulations. It begins with explorations from a single pouring point at different locations. In the next generation, the main branch starts to populate into sub-branches. Developing a production and material system. Testing CNC milling as a production system on 2D simulations. We explored the idea of negatives and positives through casting the 3D simulations. Material exploration. We began with bioplastics, but they were more appropriate for thin films rather than casting. Sand-based material exploration was conducted in different proportions and combinations, further reinforced with fibers. Natural resin-based materials were also explored, but their consistency was too thick for pouring, leading us to focus on sand-based materials. To increase resolution, we scaled up the physical experiments. The behavior and language suggested ISO surfaces, which informed further digital explorations based on the idea of marching cubes. Initial attempts tested production systems based on these digital explorations. Models were cast in pop, with foam removed using thinner. Small-scale models explored the spatial character created by this method. In further explorations, we changed the proportions of the bounding box. Each proportion resulted in different solid-to-void ratios and relationships between interior and exterior surfaces. Based on these explorations, physical models were cast at a larger scale in pop and the selected sand-based material. These informed our digital exploration in terms of density and solid-to-void ratios. In the next generation, we increased complexity in the voids formed and refined the resolution. Subsequent generations refined spatial qualities and smoothened the bounding box. In later generations, we simplified the language to establish a stronger relationship between part and whole. Each iteration added layers and changed neighborhood rule sets to achieve a desired outcome. We found spatial quality references from Ensemble Studios. Digital prototype. We reached a particular iteration with a 60% to 40% void-to-solid ratio, offering varying spatial qualities. We developed a production system where the structure could be broken into smaller parts, cast individually, and assembled. Scenario framing. The project is envisioned for semi-arid or arid regions where Earth is abundant. With scarce resources and significant construction waste, how can we build sustainably? How can we build with nature and give back to nature? We propose a structure built with sand-based materials that eventually return to the terrain. As a departure point, we explored 2 different behaviors, the reductive pattern in low-density and high-density foam. Based on these 2 directions, each of us individually developed distinct design proposals. First one, this approach explores the behavior in high-density foam. It begins with a basic setup where each cell considers 6 neighbors, with parameters explored in 3 different bounding box proportions. Resolution is increased with each generation. The horizontal bounding box was selected as it allowed full spread. In subsequent generations, the number of neighbors increased to 17 and then to 26. Neighborhood rule sets were adjusted to achieve the desired solid-to-void relationship and the highest number of stable cells. This iteration was selected as it maintained a diverse spatial character while eliminating all unstable red cells. Simultaneously, a program was developed as another layer in the process. The project is a community crafts center for local craftsmen in Rajasthan. Module determination. Pouring points determined the connection between voids. Possible modules were color-mapped based on the number of adjoining cells. Each module was analyzed based on spatial character, connectivity, and programmatic requirements. The module was selected based on programmatic needs. Parts were refined based on circulation and stability, and unstable cells were eliminated based on these rules. Space interpretation. Plans and sections illustrate how these become spaces. Interior renders showcase light quality. And contextual renders highlight the project setting. Voxel-based approach. Returning to the idea of voxels, which offer modularity, the process begins with basic pixels falling under gravity. Generations evolve to form voids as pixels stick. With increasing resolution, void formation is controlled by gravity strength. Smaller spaces are eliminated, and larger ones are divided for habitability. Structural stability was evaluated across generations. While the system builds intelligence, control is added through inputs or starting points for the code. These inputs guide the design as it evolves. Design optimization. In section views, the lower parts appear more massive and stable, reflecting optimized organization. As we move upwards, parts become more disintegrated and unstable, still shifting to find stable positions.